So let's begin looking at the compensation of op amps. What we in general want to do is make sure that omega P1, our first pole, and omega P2, our second pole, are not too close to one another in frequency. If we have a two-pole system, or at least if we assume that if we have more than two poles, that the higher order poles are much further away in frequency than the lower order poles, then we know that if we set the maximum loop gain equal, if we set the maximum loop gain such that the closed loop gain intersects the open loop gain at the second pole frequency, for instance, we're going to draw the open loop response for an operational amplifier, where we have two poles. If we set our closed loop gain such that it intersects the open loop response at the second pole frequency, we will get 45 degrees of phase margin. As we said before, 45 degrees of phase margin corresponds to the fastest settling time. Now what we want to do is set our maximum loop gain so that it intersects at this point. This will ensure that we have a stable, fast settling time at the maximum loop gain that we desire to use. One thing to ask is what configuration gives the maximum loop gain in general? So of course, the configuration that gives the max possible loop gain would be a unity gain buffer. All right, so if we take this section of the this frequency response where we have the maximum loop gain at the first pole frequency and the difference between the two pole frequencies, we could write that 20 log of omega P2 minus log of omega P1 is equal to 20 times the log of our maximum loop gain. And if we solve this, we could show that omega P2 over omega P1 would be equal to our maximum loop gain. And hence, omega P2 needs to be equal to omega P1 times the maximum loop gain that we desire in our system. Now, of course, what this all comes down to is we're going to try and design our operational amplifier to meet these kinds of considerations. So we will try and set omega P2 and omega P1 according to this formula. There are a couple of different ways that we have of doing this. So, and they're both different types of compensation. So one type of compensation would be narrowband compensation. And a second type of compensation would be pole splitting. First, let's investigate what narrowbanding is, and then we'll get to pole splitting later in the lecture. So in narrowbanding, what we're going to do is introduce a dominant pole so that there's a good separation between it and a second pole. So if we draw this graphically, you can imagine that if we have a Bode plot for our original operational amplifier, and it has some frequency response where we have some original pole and some second pole. So say we have omega P1 here and omega P2 here, and we determine that omega P1 and omega P2 are too close to one another. What we're going to do is add another pole that has a much lower frequency response than our original omega P1. So let's say that we decide we're going to lower the pole so that we get a roll-off that starts way back here in frequency. And what we're going to try and do, okay, so this is our new pole here. We'll call it omega P1 prime. And of course this is now our 20 dBs per decade roll-off. This was our original 20 dBs per decade roll-off. What we're going to do is figure out what the maximum loop gain that we're ever going to use in this configuration is, and try and get this maximum loop gain that we desire to cause the closed loop response to intersect at the old or the original omega P1. Okay, so just to summarize what we did, we added this pole omega P1, so that our closed loop gain A sub 0, our minimum closed loop gain A sub 0, intersects at omega P1, the old omega P1. All right, so we'll make a couple of comments about narrowbanding before we show an example of what narrowbanding might look like. So one remark is, we have to assume that whatever we do to create this new omega P1 doesn't move the other pole frequencies. So we'll say whatever we do to this new omega P1 doesn't have impact on our other pole frequencies. Now, this is almost never true, but maybe we can assume that whatever we do doesn't affect these very much. All right, now to ensure stability and fastest settling, we're going to choose omega P1 prime so that the magnitude of T of j omega is equal to 0 dB at the old omega P1. And of course this yields a phase margin of 45 degrees. You could see that we would get a phase shift total of 90 degrees for this first pole, and at this second pole we'd have 45 degrees for a total of 135 degrees, which is 45 degrees away from 180. Now, the other thing that we'll say is we typically would only narrowband if we have an uncompensated op amp that we're using, for instance, somebody else's uncompensated op amp. Okay, and if we knew what the original frequency response of our op amp was, we'd know how to set that omega P1 prime. It would be equal to omega P1 divided by whatever our maximum expected loop gain is. Okay, so in the next part of the lecture we'll look at an example of a type of narrowband compensation and see what you might do if you were designing for narrowband compensation, though as I said before we'd probably never use narrowbanding if we were designing our own op amp.